Picture this: a force so powerful it bends space and time. A moment when entire galaxies are torn apart and reborn, when the very fabric of reality is rewritten in an instant. Somewhere in the vast darkness of the cosmos, two celestial giants, each billions of times more massive than our sun, are hurtling toward each other, destined to collide with unimaginable violence. When they meet, the shockwaves will ripple across the universe, leaving permanent scars in the stars. This isn't science fiction. This is how our universe was built. From the very beginning, cosmic collisions have been the architects of everything we see: the birth of planets, the death of stars, even the formation of life itself. And today, we're about to embark on a journey to witness the 25 most monumental crashes in history, each one a turning point that shaped the cosmos as we know it. Think about the night sky, those glittering dots of light that seem so peaceful from here, but behind that serene facade lies a universe of chaos and creation. Every galaxy, every solar system, every atom in your body exists because of collisions, cataclysmic meetings that forged the elements, sculpted the heavens, and set the stage for life to emerge. Without these violent encounters, the universe would be an empty, silent void. And yet, for something so fundamental, these events remain some of the most mysterious and awe-inspiring phenomena science has ever uncovered. What did it look like when two black holes spiraled into each other, sending gravitational waves rippling through space-time? How did a single asteroid impact wipe out the dinosaurs and clear the way for mammals and eventually us to rise? This video is your front row seat to the most spectacular crashes in history. We'll travel back billions of years to the moment our own moon was born from the wreckage of a planet-sized collision with Earth. We'll witness galaxies merging in a dance of destruction and rebirth, stars exploding with enough force to outshine entire galaxies, and dark matter clashing in ways we're only beginning to understand. By the time we reach the end, you'll see the universe in a whole new light, not as a static backdrop, but as a living, evolving battlefield where chaos and creation are one and the same. So buckle up, the cosmos is about to show you its most explosive secrets. Before there were galaxies, before stars or planets, even before time as we know it, there was a collision unlike anything the universe would ever experience again. The Big Bang wasn't merely an explosion in space. It was space itself erupting into existence in a single, unimaginable moment of creation. Picture every particle of matter, every ripple of energy, all compressed into a space trillions of times smaller than a single atom, then suddenly unleashed in a firestorm so intense that even now, nearly 14 billion years later, we can still detect its fading echo in the faint glow of cosmic background radiation. This wasn't just the birth of matter as we know it, it was the moment the very rules of reality were written. In the first trillionth of a second, space expanded faster than light itself, a phenomenon called inflation, before cooling into a seething ocean of particles. Quarks, electrons, and photons collided in a chaotic dance, forging the first protons and neutrons. Within minutes, the universe had cooled enough for those particles to stick together, forming the nuclei of hydrogen and helium, the raw materials for every star that would ever shine. But even then, the violence wasn't over. For hundreds of thousands of years, matter and light remained locked in a brutal tug of war, scattering and crashing until finally, the universe cooled enough for atoms to form, releasing light to travel freely for the first time. Today, we see proof of this collision everywhere we look. The cosmic microwave background, the afterglow of that primordial fire, paints the entire sky in a faint, uniform glow. The ratio of hydrogen to helium in ancient stars matches predictions of nucleosynthesis from those first moments. Even the way galaxies are scattered across the cosmos echoes the tiny fluctuations in density left over from the Big Bang's chaotic aftermath. Without this collision, space would be a void without structure, without story, a blank canvas untouched by time. Every galaxy, every planet, every living thing owes its existence to that single, cataclysmic moment when the universe collided with itself and began the greatest story ever told. Long before animals walked the land or fish swam the seas, Earth witnessed a collision of an entirely different kind. One that didn't involve asteroids or planets, but something far smaller and yet infinitely more transformative. Trillions of microscopic cyanobacteria flooding the ancient oceans. This wasn't a crash of rock and fire, but a slow-motion revolution as these tiny organisms began doing something no life had done before. They exhaled oxygen. What started as a quiet biological innovation would soon escalate into a catastrophe for most life on Earth, while laying the foundation for everything that came after. Back then, around 2.4 billion years ago, our planet was a toxic wasteland by modern standards. The air was thick with methane and carbon dioxide, the oceans brimming with iron. Life existed, but it was primitive, anaerobic microbes thriving in the absence of oxygen. Then cyanobacteria evolved photosynthesis, harnessing sunlight to create energy and releasing oxygen as waste. At first, this new gas simply dissolved into the water, reacting with iron to form rusty bands we still find in ancient rock layers today. But eventually, the seas could hold no more, and oxygen began bubbling into the atmosphere, an environmental disaster for organisms that had evolved without it. The aftermath was brutal. Oxygen was poison to most early life, triggering the planet's first mass extinction event. Methane-eating bacteria died off, collapsing Earth's greenhouse effect and plunging the planet into a glaciation so severe it's been called Snowball Earth. But in this chaos lay the seeds of complexity. Oxygen's reactive nature made possible new, more efficient energy production in cells, the foundation for multicellular life. Over eons, surviving organisms adapted, giving rise to mitochondria, the powerhouses of complex cells. Without this collision between biology and chemistry, animals, including us, would never have had the energy to evolve beyond single-celled simplicity. Today, we see echoes of this event everywhere. The iron-rich rocks that captured oxygen's rise now form vast mineral deposits. The very air we breathe, 21% oxygen, is a direct result of that ancient microbial revolution. Even the chloroplasts in plants trace their ancestry back to those pioneering cyanobacteria. It's a reminder that sometimes the most universe-shaping collisions aren't the loudest or most violent, but the quiet, persistent ones that rewrite the rules of existence itself. 4.5 billion years ago, our solar system was a demolition derby of newborn planets, a chaotic free-for-all where survival meant growing fast or being destroyed. In this primordial frenzy, Earth barely survived its most violent encounter, a head-on crash with Theia, a rogue planet the size of Mars. The impact was so colossal it vaporized mountains, liquefied entire continents, and nearly tore our world apart. Yet from this destruction emerged something that would make Earth unique among planets, our moon. Picture the moment of impact. Theia, named after the mythical Greek Titan who birthed the moon goddess Selene, slammed into early Earth at a sharp angle, striking with the force of trillions of atomic bombs. The collision was so violent it melted both worlds into a single swirling mass of molten rock and metal, ejecting a searing tidal wave of debris into space. For weeks, Earth's surface was an ocean of magma under a sky choked with glowing fragments, the beginning of a planetary ring system unlike anything in our solar system today. Over time, gravity sculpted this debris into a new celestial body, locking it into orbit as our moon. But this crash did far more than create a pretty night light. It gave Earth the gift of stability. Before the impact, our planet wobbled wildly on its axis, swinging between extreme seasons that would have made complex life nearly impossible. The moon's gravity became an anchor, steadying Earth's tilt to a gentle 23.5 degrees. the perfect angle for stable climates and predictable seasons. And when that newborn moon settled into orbit just 15,000 miles away, 10 times closer than today, its gravitational pull churned Earth's oceans into furious tides, stirring the chemical soup of life and possibly jump-starting evolution itself. Evidence of this cataclysm is written in stone and in space. Moon rocks brought back by Apollo astronauts have nearly identical oxygen isotope ratios to Earth's mantle, proving both worlds share the same primal material. The Moon's iron core is suspiciously small, just as scientists predicted for an impact-borne satellite. Even Earth rotation speed, the 24-hour day we take for granted, is a direct result of that ancient collision's angular momentum. Without this violent beginning, our days might last just 8 hours, with hurricane-force winds ripping across the surface. Perhaps most remarkably, the Moon continues to shape life today. Its tides mix nutrients in coastal waters, creating fertile nurseries for marine species. Its gravitational pull may have guided the first fish to venture onto land, setting the stage for terrestrial evolution. Even the length of our months traces back to that impact, the 29-day lunar cycle synchronized with biological rhythms, from coral spawning to human fertility. So the next time you gaze at the Moon, remember, it's not just a companion in the sky, it's the scar of a collision that turned Earth from just another rocky planet into the only known cradle of life in the universe. Just when Earth had begun to recover from the Moon-forming impact, another wave of destruction came crashing down, this time from the depths of space. Between 4.1 and 3.8 billion years ago, the solar system descended into chaos during an era known as the Late Heavy Bombardment. Imagine trillions of asteroids and comets, some as large as cities, hurtling toward the inner planets in a relentless storm of fire and ice. Earth, still cooling from its molten infancy, endured impacts so violent they vaporized entire oceans and melted the young crust anew. Yet hidden in this devastation were the very ingredients that would one day spark life. The bombardment likely began when the giant planets Jupiter, Saturn, Uranus, and Neptune shifted their orbits in a gravitational dance. This migration destabilized the asteroid belt, flinging debris inward like cosmic shrapnel. On Earth, evidence of this period has been erased by plate tectonics, but the Moon's scarred surface tells the story. Its oldest craters, like the 850-mile-wide South Pole Aitken Basin, date back to this era, preserved in silent testimony to the violence. Scientists estimate Earth suffered 10 times more impacts than the Moon due to its stronger gravity, meaning some asteroids would have released enough energy to boil the atmosphere and sterilize the surface repeatedly. But these cataclysms carried a paradoxical gift: water. Chemical fingerprints in ancient rocks suggest much of Earth's oceans arrived during the bombardment, locked inside icy comets and water-rich asteroids. When these frozen time capsules slammed into the planet, they released their precious cargo, filling basins carved by earlier impacts. Even more remarkably, some asteroids carried organic molecules, amino acids and nucleotides, the building blocks of proteins and DNA. The Murchison meteorite, a relic of this era found in Australia, contains over 90 different amino acids, proving space rocks could ferry life's raw materials. The bombardment didn't just deliver ingredients, it stirred the pot. Impact-generated heat created hydrothermal vents where warm, mineral-rich water circulated through fractured rock, providing ideal conditions for chemistry to become biology. Some theories suggest life may have started and been wiped out multiple times during this period, with each extinction clearing the stage for more complex experiments in evolution. By the time the storm subsided, Earth had transformed from a hellish wasteland into a water world teeming with potential, a testament to how destruction and creation are two sides of the same cosmic coin. Today, we see echoes of this epoch everywhere, the gold in your jewelry likely delivered by asteroid impacts during the bombardment, the salt in our oceans, a remnant of dissolved minerals from ancient space rocks. Even the continents themselves may owe their size to this era, as massive impacts cracked the crust and triggered volcanic outpourings that built the first landmasses. It's a humbling thought. The same collisions that nearly obliterated early Earth also set the table for life's grand feast. Deep in the swirling chaos of the early solar system, something unprecedented was taking shape, a gravitational monster so massive it would forever alter the fate of every planet. Jupiter didn't just form, it devoured its way into existence through a relentless series of collisions, growing from a pebble to a behemoth in a cosmic feeding frenzy. While Earth was still a molten speck, Jupiter's core was already hoarding material at a staggering rate, vacuuming up gas, dust, and even other budding protoplanets with its ever-strengthening pull. This insatiable appetite didn't just make Jupiter king of the planets, it turned the gas giant into the solar system's ultimate protector, a gravitational shield that has safeguarded life on Earth for billions of years. The process began with tiny ice-covered grains sticking together in the cold outer reaches of the protoplanetary disk. As these clumps grew to boulder size, then mountain size, their gravity accelerated, pulling in more material at exponential rates. Scientists estimate Jupiter's core reached 20 times Earth's mass within just 1 million years, a blink in cosmic time. That's when the real feast began. The core's gravity became strong enough to capture hydrogen and helium directly from the surrounding nebula, swelling Jupiter into the first true planet. But this growth wasn't gentle. Countless smaller bodies, some as large as Mars, slammed into the growing giant, releasing enough energy to briefly outshine the young sun. One particularly massive collision may explain why Jupiter's core is less dense and more diffuse than expected, as if something punched through it like a bullet through fog. What makes Jupiter truly extraordinary isn't just its size, it's how its gravity reshaped the solar system's architecture. Acting like a cosmic vacuum cleaner, Jupiter's immense pull ejected rogue asteroids into deep space or sucked them into its swirling clouds. Without this gravitational policing, Earth would still be bombarded by deadly impacts every few centuries. The evidence is written in the asteroid belt. That rocky debris field between Mars and Jupiter should contain another planet's worth of material, but Jupiter's gravity prevented anything substantial from forming there. Even today, Jupiter continues to protect us. In 1994, the world watched as comet Shoemaker-Levy 9, torn apart by Jupiter's tides, slammed into its atmosphere with the force of 600 times Earth's nuclear arsenal, a direct hit that would have sterilized our planet. Modern telescopes revealed Jupiter still catching asteroids like a celestial goalie. In 2019 alone, amateur astronomers recorded 19 fireballs in Jupiter's atmosphere, impacts that would have been extinction-level events on Earth. Yet Jupiter's protection isn't absolute. Some rocks still slip through its gravitational net, like the dinosaur-killing asteroid that struck Earth 66 million years ago. But statistically, Jupiter intercepts about 99% of would-be impactors headed our way. Without this gas giant standing guard, complex life might never have had the stable environment needed to evolve beyond single-celled organisms. So while Jupiter may seem like a distant, stormy giant, it's actually Earth's oldest and most powerful guardian, a silent sentinel forged through countless collisions, watching over us from the outer darkness. Saturn's rings glow like a cosmic crown, one of the most breathtaking sights in our solar system, but their beauty hides a violent birth. These shimmering bands of ice and rock didn't form gently. They're the shattered remains of a moon that wandered too close to the gas giant's crushing embrace, torn apart in a cataclysmic showdown between gravity and resilience. The story likely begins with an icy moon similar to Titan or Enceladus, orbiting peacefully until some cosmic nudge, perhaps a collision with another object or a gravitational tug from a passing planet, sent it spiraling inward. As it crossed Saturn's Roche limit, the point where tidal forces overpower a moon's own gravity, the satellite's fate was sealed. Imagine the moon stretching like taffy, its icy shell fracturing first, then its rocky core disintegrating into rubble. Within days, what was once a cohesive world became a swirling disk of debris, its pieces trapped in orbit like moths around a flame. Today, the rings tell forensic tales of that destruction. Their composition, 95% pure water ice, matches Saturn's icy moons, not the dust-rich material of the early solar system. The rings are also suspiciously young. Data from NASA Cassini mission suggests they formed between 10 and 100 million years ago, a blink in cosmic time. Even their structure hints at violence, gaps carved by shepherd moons, spiral density waves frozen in place, and bizarre propeller-shaped disturbances where tiny moonlets plow through the debris like ships through fog. But the most chilling clue, Saturn's rings are disappearing. Micrometeoroid impacts and solar radiation slowly erode them, dragging ice particles toward the planet in a ring rain that dumps enough water to fill an Olympic-sized pool every half hour. At this rate, the rings may vanish entirely in another 300 million years, a fleeting masterpiece by cosmic standards. So while we marvel at their grandeur today, we're witnessing just a single frame in a much longer saga of creation and dissolution, where even the most majestic structures are born from chaos and destined to fade. Far from the orderly dance of planets we see today, early Uranus was once struck a blow so violent it never recovered, a hit so powerful the entire planet was knocked sideways, forever altering its destiny. Unlike every other planet in our solar system, Uranus rotates nearly perpendicular to its orbit, spinning like a top that's been toppled over, with its poles facing the Sun for decades at a time. This bizarre orientation isn't some quirk of formation, it's the cosmic equivalent of a knockout punch, the result of a head-on collision with an object at least twice the mass of Earth. Scientists reconstruct this ancient cataclysm through clues frozen in Uranus' present-day chaos. The impactor, likely a fledgling protoplanet, slammed into Uranus with such force it rewrote the planet's angular momentum, tilting its rotational axis by a staggering 98 degrees. Debris from the collision may have coalesced into Uranus' irregular moons, which orbit in the same extreme tilt, while shattered remains could explain the planet's unusually sparse ring system compared to Saturn's. Even Uranus' magnetic field betrays this trauma, offset by 60 degrees from its rotational axis and drastically off-center, as if the planet's internal dynamo was permanently scrambled by the blow. The consequences of this tilt are dramatic. Each Uranian pole experiences 42 Earth years of continuous sunlight followed by 42 years of darkness, creating the most extreme seasons in the solar system. During Voyager 2's 1986 flyby, Uranus' south pole was pointed almost directly at the Sun, leaving the northern hemisphere in a frigid twilight. This perpetual imbalance warps atmospheric circulation, driving supersonic winds that reverse direction between hemispheres and trapping heat in ways we're still struggling to model. Yet Uranus' misfortune may be our gain. The impact likely blasted water and organic molecules deep into space, some of which could have hitchhiked to Earth on comets. More fundamentally, studying Uranus' tilt helps us understand how common such violent encounters were in the early solar system and how frequently they might occur around other stars. When astronomers discovered exoplanets with similarly extreme tilts, Uranus became the benchmark for understanding these distant worlds. Its sideways spin, once seen as a cosmic oddity, is now recognized as a vital clue in unraveling the chaotic adolescence of planetary systems everywhere. The next time you gaze at the night sky, remember Uranus' silent, sideways roll is more than a curiosity. It's a planetary scar, a monument to the violence that shaped our cosmic neighborhood, and a reminder that even giants can be humbled by the universe's relentless collisions. The reign of the dinosaurs ended not with a whimper but with a fireball brighter than a million suns. 66 million years ago, a 6-mile-wide asteroid, a mountain of rock moving 20 times faster than a bullet, slammed into what's now Mexico's Yucatan Peninsula. In less than a second, the impact released more energy than all nuclear weapons ever built combined, vaporizing thousands of cubic miles of rock and punching a crater over 110 miles wide. The shockwave flattened forests across continents, while mega tsunamis several miles high scoured coastlines thousands of miles away. Yet these immediate horrors were just the opening act of an extinction event that would erase 75% of all species on Earth. Dinosaurs had ruled for 160 million years, surviving ice ages and volcanic upheavals, but nothing prepared them for the hellscape that followed this impact. The real killer came from the skies, as trillions of tons of vaporized rock rained back down. Friction heated the atmosphere until it glowed like an oven coil, igniting global firestorms that turned forests to ash. Soot and sulfur aerosols blotted out the sun for years, collapsing food chains as photosynthesis stopped. Acid rain turned oceans corrosive, while temperature swings of 50 degrees Fahrenheit between day and night made survival nearly impossible for warm-blooded giants. But in this devastation lay opportunity. Small, burrowing mammals, some no larger than rats, survived where towering predators could not. Sheltering underground, living off seeds and insects, these resilient creatures inherited a world emptied of dominant competitors. With dinosaurs gone, mammals diversified explosively, evolving into everything from bats to whales within 10 million years. Even the asteroid's target proved fateful. The Yucatan's sulfate-rich rocks amplified climate effects, while an impact just minutes earlier or later might have hit deep ocean, causing less extreme cooling. Today, the evidence is etched in stone worldwide. A thin layer of iridium, rare on Earth but abundant in asteroids, marks the exact moment of impact in geological strata. In Hell Creek, Montana, dinosaur fossils appear right up to this KT boundary, then vanish. The crater itself, named Chicxulub after a nearby Mayan village, remained hidden under limestone for 65 million years until oil drillers noticed strange circular gravity anomalies in the 1970s. Perhaps most haunting is how narrowly we escaped oblivion. Had the asteroid arrived a few million years earlier, when mammals were less adaptable, or later, when primates had evolved further, human ancestors might not have made it. This collision didn't just change life on Earth, it made our existence possible, proving that sometimes extinction is the universe's most creative force. The same violence that erased giants cleared the stage for a new act in evolution's play, one where small, clever creatures would eventually look up at the stars and wonder about the impact that started it all. 66 million years ago, Earth's fate hinged on a cosmic bullet, a 6-mile-wide behemoth of rock and metal screaming through space at 45,000 miles per hour. This wasn't just any asteroid. Chicxulub, as we now call it, carried the kinetic energy of 10 billion Hiroshima bombs, and when it struck shallow waters off what's now Mexico's Yucatan Peninsula, the collision didn't just shake the planet, it rewrote the rules of life itself. The first second of impact was pure physics turned nightmare. The asteroid vaporized on contact, boring a hole 20 miles deep into Earth's crust while ejecting a superheated jet of plasma that scorched the atmosphere. Shockwaves radiated outward at hypersonic speeds, liquefying bedrock hundreds of miles away and sending seismic waves circling the globe like a struck gong. But the real horror came from the ocean. Water displaced by the impact surged outward in tsunamis taller than the Empire State Building, racing across the Gulf of Mexico at jetliner speeds. Sediment cores from Louisiana show layers of debris dumped by waves that traveled over 1,000 miles inland, carrying fossilized marine creatures deep into what should have been safe terrestrial ground. Then came the long winter. The impact blasted 25 trillion metric tons of debris into orbit, enough to blanket the entire planet in a foot-thick layer of ash. Sulfur-rich vaporized rock combined with water vapor to form a global haze of sulfuric acid droplets, blocking 90% of sunlight for up to a decade. Global temperatures plunged by as much as 50 degrees Fahrenheit, freezing tropical plants where they stood while acid rain turned oceans lethal. Deep-sea drill cores reveal a thin layer of soot just above the impact boundary, the charred remains of continents set ablaze by superheated debris re-entering the atmosphere. Yet some creatures weathered the apocalypse. Crocodiles, with their slow metabolisms and ability to go months without food, became unlikely survivors. Birds, the last living dinosaurs, endured thanks to their small size and diverse diets. And beneath the scorched earth, burrowing mammals and insects clung to life in insulated nests, emerging into a world where the giants were gone and evolution's stage stood empty. Chicxulub's true legacy isn't just destruction, it's opportunity. The same impact that silenced the dinosaurs' reign cleared ecological niches for mammals to explode in diversity, setting the timeline that would eventually lead to primates, hominids, and us. Every human achievement rests on the foundation of that catastrophic collision, a reminder that sometimes the universe moves forward not through gentle steps, but through shattering impacts that redefine what's possible. Between Mars and Jupiter lies a cosmic shooting gallery, the asteroid belt, where millions of rocky fragments orbit in perpetual limbo. This isn't just debris, it's the graveyard of a planet that never was, a world torn apart before it could form, all because of Jupiter's gravitational tyranny. Billions of years ago, as the solar system took shape, this region should have coalesced into a fifth rocky planet. The raw materials were there, enough dust and rock to build another Earth-sized world. But Jupiter, already a gas giant in the making, had other plans. Every time fledgling planetesimals in the belt began clustering together, Jupiter's immense gravity yanked them apart like an invisible hand smashing pottery. Some were flung into the sun or ejected into interstellar space, while others shattered in violent collisions, creating the fragments we see today. The evidence is written in the belt's chaotic dynamics. Most asteroids orbit in gaps called Kirkwood Gaps, regions where Jupiter's gravitational resonance makes stable orbits impossible. These aren't random empty spaces. They're gravitational kill zones where any object lingering too long gets hurled toward the inner solar system. Even the belt's total mass tells a story. All its asteroids combined amount to less than 4% of our moon's mass, a pittance compared to what should have been a full-fledged planet. Yet this gravitational oppression has an upside. The asteroid belt acts as a cosmic buffer, its inhabitants mostly contained by Jupiter's influence. Without this control, Earth would face catastrophic impacts daily. Instead, we get occasional strays like the 10-kilometer-wide dinosaur killer. While Jupiter intercepts or deflects most threats, ironically, these leftover fragments are now treasures. Meteorites from the belt contain amino acids and water, hinting they delivered life's building blocks to Earth. And as spacecraft like OSIRIS-REx probe asteroids like Bennu, we're uncovering time capsules from the solar system's birth, pristine records of the violent processes that shaped our cosmic neighborhood. The asteroid belt isn't just debris. It's a monument to Jupiter's power, a reminder of the planet we lost, and a celestial museum preserving the chaos from which our stable world emerged. Right now, from our quiet corner of the Milky Way, Andromeda appears as nothing more than a faint smudge in the night sky, a spiral of stars 2.5 million light-years away. But this peaceful distance is an illusion. Hurtling toward us at 250,000 miles per hour, Andromeda is destined to become the most spectacular wrecking ball in cosmic history. In roughly 4 billion years, these two galaxies will collide in a gravitational tango that will tear apart the night sky as we know it. And yet, remarkably, Earth might just survive the chaos. The first changes will be subtle. Over the next 2 billion years, Andromeda will grow from a dim blob to a brilliant swirl dominating the heavens. Then comes the gravitational onslaught. As the galaxies close in, their mutual pull will warp their shapes like taffy, stretching spiral arms into long, luminous streamers. Stars won't actually collide, space is too vast, but their orbits will be flung into chaos. Our solar system could be hurled toward the galactic center or ejected into the outer darkness. The night sky will transform into a fireworks show of unprecedented scale, with newborn stars igniting in shockwaves of gas and dying supernova outshining entire constellations. The climax arrives when the galactic cores, each harboring a supermassive black hole, begin their death spiral. For millions of years, these monsters will circle each other, shredding nearby stars and belching radiation across the electromagnetic spectrum. Eventually, they'll merge in a burst of gravitational waves, rocking the fabric of spacetime itself. The resulting elliptical galaxy, nicknamed Milky will be a featureless blob of aging stars, its spiral elegance erased forever. Yet through it all, planets may endure. Simulations suggest our solar system has a 50% chance of being flung farther into the galactic outskirts, but only a 3% chance of ejection. The real threat isn't the collision. It's the sun, which by then will have swollen into a red giant, likely vaporizing Earth. But if humanity has migrated elsewhere, our descendants might witness this cosmic ballet from a safe distance, watching as two islands of stars that once seemed eternal become something entirely new. This collision isn't destruction, it's rebirth. Galaxies grow by devouring others, and Milky may one day feast on smaller neighbors too. What we're seeing isn't the end of our galaxy's story, but the next chapter in an epic that began with the Big Bang and will continue long after Earth is gone. The universe writes its history in collisions, and this one, slow, stately, and inevitable, will be among its most majestic. The universe keeps its most important secrets hidden in plain sight, and nowhere is this more evident than in the Bullet Cluster, a cosmic collision that ripped the mask off dark matter. Two massive galaxy clusters, each containing hundreds of galaxies, slammed into one another at speeds surpassing 20 million miles per hour, creating a cosmic wreck so violent it revealed an invisible hand shaping the universe. When astronomers first studied this system with optical telescopes, they saw chaos galaxies strewn across millions of light years like shrapnel from an explosion. But the real story emerged when they looked deeper. X-ray telescopes captured a ghostly glow of superheated gas, the ordinary matter from both clusters that had collided and pooled at the collision center like water in a bowl. Then came the shocker. Gravitational lensing maps showed most of the mass wasn't where the gas was. Instead, it lurked near the galaxies themselves, bending light from background objects as if invisible anchors were holding them in place. This was dark matter caught in the act. Unlike normal matter, these mysterious particles didn't slow down during the collision. They sailed right past each other, carrying the bulk of the cluster's mass with them. The gas, slowed by electromagnetic interactions, lagged behind. For the first time, we had a clear separation between ordinary matter and the unseen stuff that outweighs it 5-1. It's as if two crowds of people ran into each other, but only their shadows kept moving forward while their bodies got stuck. The implications were staggering. This cosmic accident proved dark matter isn't just a theoretical placeholder. It's real, it's dynamic, and it shapes the universe's structure on the largest scales. Without its gravitational scaffolding, galaxies would fly apart, and clusters like this one could never form. The Bullet Cluster became a smoking gun, silencing skeptics who argued dark matter might just be a flaw in our understanding of gravity itself. Yet the mystery only deepens from here. Why doesn't dark matter interact with light or ordinary matter? What particles compose it? The collision left clues but no answers, only proof that we're surrounded by an invisible ocean of mass, its waves guiding the visible universe like currents steering ships at sea. Every galaxy, every star, every atom in your body moves under the influence of this enigmatic force, and it took a catastrophic intergalactic pileup to show us it was there all along. Now, when astronomers study other merging clusters, they find the same eerie separation, dark matter leading the charge while gas trails behind in glowing ribbons. Each collision is a forensic snapshot, revealing how the unseen architecture of the cosmos behaves under extreme conditions. The bullet cluster didn't just prove dark matter exists, it gave us a new way to study the universe's hidden framework, one cosmic crash at a time. Some of the universe's most spectacular fireworks don't come from explosions but from slow-motion cosmic car crashes. 60 million light-years away, two spiral galaxies known as the antennae galaxies are locked in a gravitational embrace that's rewriting their futures. Unlike the instantaneous impacts of asteroids or planets, galactic collisions unfold over hundreds of millions of years, transforming graceful spirals into chaotic stellar nurseries where new suns ignite by the millions. Through telescopes, the antennae galaxies look exactly as their name suggests, two long, luminous streams of stars stretching outward like insect antennae. These are tidal tails, each over 300,000 light-years long, formed as gravitational forces rip stars and gas from the galaxy's outer edges. But the real action lies at the collision's heart, where the galaxy's cores are circling each other in an ever-tightening spiral. Here, vast clouds of interstellar gas, compressed by the collision's shockwaves, collapse under their own weight, igniting clusters of massive blue stars that burn bright and die young in supernova explosions. What makes this collision extraordinary is its creative destruction. Normally, spiral galaxies like our Milky Way form stars at a leisurely pace, perhaps 1 or 2 per year. But in the antennae system, astronomers detect over 100 new stars igniting annually, with some superstar clusters containing millions of suns packed into regions just a few light-years across. These stellar fireworks are fueled by the collision's unique geometry. The galaxies didn't hit head-on but grazed each other at an angle, creating overlapping shock fronts that squeeze gas like a cosmic accordion. Yet this frenzy won't last forever. In about 400 million years, the antennae galaxies will complete their merger, leaving behind a single elliptical galaxy devoid of spiral arms, a featureless island of aging stars. All that frenetic star formation will cease as the last gas reserves are either consumed or blown away by supernova winds. What began as two elegant spirals will end as a stellar retirement home, its brightest stars long since burned out. For astronomers, the antennae offer more than just a light show, they're a preview of our own galaxy's fate. When the Milky Way collides with Andromeda in 4 billion years, similar processes will unfold on our cosmic doorstep. By studying how gas behaves in the antennae system, how star clusters form and disperse, and how metals from supernova enrich future generations of stars, we're reading the instruction manual for our own distant future. The antennae remind us that in the universe, endings are also beginnings. The same forces that tear galaxies apart also create the conditions for new stars and potentially new planets to form. Every atom in our bodies was forged in such cosmic violence, proving that creation and destruction are two sides of the same celestial coin. The tadpole galaxy doesn't just drift through space, it wears its violent history like a badge of honor, stretching a luminous tail of stars nearly 300,000 light-years behind it like a cosmic comet. This isn't some delicate spiral or bloated elliptical. It's a galaxy caught mid-transformation, its graceful disk distorted by a smaller intruder that barreled through its heart millions of years ago. The result, one of the longest stellar streams ever observed, a glittering scar testifying to the chaos that reshapes galaxies when they collide. Hubble's sharp eye captured the tadpole's drama in stunning detail. A bright, disrupted core surrounded by rippling waves of gas and dust, with that extraordinary tail trailing off into intergalactic space. The tail itself is a stellar graveyard and nursery combined. Older stars ripped from the main galaxy during the collision mingle with brilliant blue clusters born from gas compressed during the violent encounter. These newborn stars blaze with youthful intensity, their ultraviolet light ionizing surrounding hydrogen into glowing pink nebulae that dot the tail like cosmic streetlights. What makes the tadpole particularly fascinating is the forensic evidence of its assailant. Unlike messy mergers that leave both galaxies unrecognizable, this was a high-speed encounter, a cosmic hit and run. The smaller galaxy, likely a dwarf, punched through the tadpole's disk at such velocity that it escaped largely intact, leaving behind only gravitational fingerprints. Computer simulations suggest the intruder now lies about 250,000 light-years ahead of the tadpole, still fleeing the scene of the crime. The collision's aftermath offers astronomers a rare laboratory to study how galaxies recycle material. As the tail stars gradually disperse, some may form a halo around the tadpole, while others could become intergalactic wanderers adrift in the void. Meanwhile, the main galaxy's distorted arms will take hundreds of millions of years to settle if they ever do. Unlike the antennae galaxy's slow dance, the tadpole's encounter was a brief, violent yank, proving galaxy evolution isn't always a gradual process. Yet the most profound lesson lies in the tail's sheer length. Stretching twice the diameter of our Milky Way, this stellar river reminds us how far gravity's influence reaches. Even as the galaxies separate, their gravitational connection persists, weaving new structures across unimaginable distances. The tadpole isn't just a snapshot of destruction. It's a living monument to the invisible threads that bind the universe together, one collision at a time. Far beyond the tadpole's lonely tail, another pair of galaxies performs an even more intricate dance, two spirals locked in a gravitational embrace so tight they've earned the nickname the Mice Galaxies. Unlike the tadpole's brief encounter, this collision unfolds in ultra-slow motion, a cosmic ballet that will take hundreds of millions of years to reach its climactic merger. Through the Hubble Space Telescope, we witness their long tails of stars and gas stretching over 160,000 light-years, twin rivers of cosmic debris, marking their shared fate as they spiral inevitably toward unity. What makes the Mice Galaxies remarkable isn't just their striking visual similarity to scurrying rodents, it's the textbook example they provide of how galactic mergers unfold in stages. Currently, the two spirals are about 25,000 light-years apart, close enough for their mutual gravity to shred their outer disks. The tails themselves tell a forensic story, composed primarily of older stars and gas stripped from the galaxy's outskirts. They're not just debris trails, but cosmic breadcrumbs marking the path of their gravitational interaction. Unlike the tadpole's lopsided collision, the mice are meeting more evenly, their disks warping symmetrically as tidal forces redistribute material like taffy being pulled apart. Star formation paints another layer onto this evolving masterpiece. While the galaxy's cores remain relatively calm for now, compressed gas along their colliding edges ignites new stellar nurseries at a rate dwarfing anything seen in isolated spirals. Infrared observations reveal hidden bursts of star formation obscured by dust clusters so young and massive they resemble miniature versions of the universe's first star factories. Yet this flurry of creation is fleeting. As the galaxies continue merging, turbulence will scatter these star-forming regions, while feedback from supernova and black holes blows away remaining gas like cosmic winds clearing fog. The mice also offer a preview of galactic recycling on an epic scale. Simulations suggest much of the material in those spectacular tails will eventually fall back into the merged galaxy, while some may form a diffuse halo or even give birth to dwarf galaxies, celestial offspring of the collision. Even the supermassive black holes at their centers will join the dance, spiraling toward each other over hundreds of millions of years until they too merge in a burst of gravitational waves. Unlike the antennae's head-on crash or the tadpole's hit and run, the mice showcase a prograde encounter, their disks rotating in the same direction they're orbiting each other. This alignment creates smoother, more drawn-out distortions compared to other merger types. It's a reminder that no two galactic collisions are identical. Each has its own rhythm, its own unique fingerprint in the cosmos. For astronomers, the mice serve as a living time lapse. At 300 million light-years away, we're seeing them as they were during Earth's Carboniferous period when towering fern forests dominated land and the first reptiles evolved. By the time their merger completes, our Sun may have already ballooned into a red giant. Yet this staggering timescale is what makes them so valuable. They let us study a single frame of a process that outlasts entire species, offering clues to how our own Milky Way will transform when Andromeda arrives. The mice don't just collide, they whisper the future of every galaxy caught in the universe's slow, inevitable dance of destruction and renewal. Among the countless galaxies spinning through the cosmos, the Cartwheel Galaxy stands out like a celestial bullseye, a perfect ring of newborn stars encircling a golden core. This isn't some gentle cosmic artwork. It's the aftermath of a high-speed galactic strike, where a smaller galaxy punched straight through the Cartwheel's heart like a bullet through smoke, leaving ripples of starbirth in its wake. The collision happened roughly 200 million years ago, a blink in cosmic time, when a dwarf galaxy one-third the Cartwheel's size came screaming through at nearly 200,000 miles per hour. The intruder didn't merge or stick around. It blasted clean through the larger galaxy's disk, sending shockwaves racing outward like ripples from a pebble dropped in a pond. These waves compressed vast clouds of hydrogen gas as they traveled, triggering a firestorm of star formation in an expanding ring that now measures 150,000 light-years across. Hubble's sharp eye reveals this ring dotted with thousands of brilliant blue star clusters, each one a stellar nursery where stars ignite 10 times faster than in our Milky Way. What makes the Cartwheel extraordinary isn't just its shape, it's a living experiment in galactic physics. The inner golden core represents the older population of stars that survived the collision relatively unscathed, while the outer ring showcases the galaxy's frantic rebirth. Between them lies a barren gap nearly devoid of gas, the cosmic dead zone, where the shockwave swept material outward like a snowplow clearing a road. Radio telescopes detect carbon monoxide molecules tracing this expelled gas, showing how the collision redistributed the galaxy's raw materials in real time. But the drama doesn't end there. The violent encounter likely stripped away much of the Cartwheel's dark matter halo, the invisible gravitational scaffolding that keeps galaxies intact. Computer simulations suggest this loss may doom the galaxy's distinctive shape, as without dark matter's stabilizing influence, the ring structure could unravel over billions of years. Even now, filaments of gas stretch between the Cartwheel and its two smaller companion galaxies, evidence of ongoing gravitational interactions that continue reshaping this cosmic accident. For astronomers, the Cartwheel is more than a pretty face, it's a Rosetta Stone for understanding how collisions drive galactic evolution. Similar ring galaxies are vanishingly rare, suggesting most intruders don't hit with the perfect speed and angle needed to create such symmetrical shockwaves. By studying how star formation ignites in these expanding waves, how gas cools and collapses under extreme conditions, and how galaxies recover from such violent encounters, we're glimpsing the processes that built the diverse galactic menagerie we see today. The Cartwheel's lesson is clear. Even the most destructive cosmic events can spark creation. From the chaos of collision comes structure, from destruction comes new light, a reminder that the universe writes its grandest stories through catastrophe. Deep in the constellation Ursa Major, a celestial oddity lurks, a galaxy so bizarre it earned the nickname Space Invader for its uncanny resemblance to the classic arcade game's pixelated aliens. Officially catalogued as Mayow's object, this cosmic Rorschach test isn't some trick of perspective. It's the smoking gun of a hypervelocity galactic collision that warped two normal spiral galaxies into an intergalactic abstract painting. What makes Mayow's object so extraordinary is the violence of its birth. Unlike slow-motion mergers like the mice galaxies, This was a high-speed side-swipe, two galaxies passing through each other at over 2 million miles per hour, a velocity so extreme it should have ripped them apart. Instead, their gravitational embrace stretched and twisted their structures into a shape that defies textbook classifications. Hubble's razor-sharp imaging reveals 4 luminous knots, the remnants of the galaxy's cores connected by streams of young blue stars that form the invader's iconic jagged outline. These stellar tendrils act as cosmic breadcrumbs, tracing the paths of material flung outward by centrifugal forces during the collision. The real forensic evidence lies in the gas. While stars themselves rarely collide during galactic encounters, the galaxy's interstellar gas clouds slam together like celestial fog banks, triggering explosive waves of star formation. In Mayall's object, astronomers detect these stellar fireworks concentrated along the collision's shock front, a band of superstar clusters glowing so intensely they outshine entire galaxies. Yet just behind this wave of creation lies a bizarre void, a region nearly devoid of gas where the collision's turbulence has swept material clean like a cosmic squeegee. This peculiar structure challenges long-held assumptions about galactic resilience. Conventional wisdom suggested such high-speed encounters would leave galaxies largely unchanged, like ships passing in the night. But Mayall's object proves even glancing blows can completely remodel galactic architecture when conditions align. Its persistence over hundreds of millions of years demonstrates how gravity binds even violently disrupted systems together, a testament to dark matter's invisible scaffolding keeping the wreckage from dispersing entirely. For scientists, this cosmic oddity serves as a controlled experiment in extreme physics. The collision happened nearly perfectly edge-on from our viewpoint, creating a clean laboratory to study shockwave dynamics in galactic gas. Its unusual geometry also helps calibrate computer simulations when modelers input the observed speeds and angles. Their virtual collisions must reproduce the space invader's exact shape to be considered accurate. More fundamentally, Mayall's object hints that such violent encounters might be more common than we thought. In the early universe, when galaxies were packed closer together, high-speed collisions could have been a major driver of galactic evolution. Some astronomers speculate similar events may explain certain ultra-diffuse galaxies, ghostly collections of stars that seem to have lost most of their gas through ancient, traumatic encounters. As we continue discovering more of these galactic wreckage fields across the cosmos, each one adds another piece to the puzzle of how collisions shaped and continue shaping the universe's grand structure. The space invader's greatest lesson: even the most chaotic cosmic accidents follow hidden rules, and sometimes destruction creates forms more marvelous than anything gravity could build alone. Deep in the constellation Ophiuchus, a cosmic monster stirs NGC 6240, a galaxy so warped by violence it glows with the light of over 300 billion suns. This isn't just one galaxy, but a trio of smaller spirals that collided in a gravitational melee so chaotic it birthed something entirely new. Most galactic mergers involve two players, but here, astronomers found evidence of a rare three-way pileup, with the wreckage still smoldering in infrared light 150 times brighter than our Milky Way. The first clues came from its grotesque shape: no elegant spiral arms or smooth elliptical halo, but a twisted mass of dust and gas stretching over 300,000 light-years, riddled with filaments and loops like cosmic taffy pulled in every direction. But the real surprise lay at its heart. Instead of a single supermassive black hole, Hubble and Chandra X-ray Observatory revealed not two, but 3 monstrous nuclei lurking within, each the remnant core of one of the original galaxies, now orbiting so close they're practically rubbing event horizons. 2 of these black holes, each weighing over 90 million suns, are separated by just 3,000 light-years, close enough to exchange matter in swirling rivers of stolen gas. This proximity makes NGC 6240 a ticking time bomb, over the next few 100 million years, those black holes will spiral closer through gravitational radiation, eventually colliding in an explosion so powerful it will shake the fabric of space-time across the entire universe. Such mergers are among the most energetic events since the Big Bang, capable of blasting gravitational waves strong enough to distort matter millions of light-years away. Yet, even before that final crash, their cosmic dance is rewriting physics textbooks. The surrounding gas, heated to millions of degrees by friction and shock waves, creates a superwind blowing outward at 2 million miles per hour, a storm so intense it's sterilizing entire regions of the galaxy from future star formation. What makes this collision unique isn't just its violence, it's the window it offers into galactic evolution's most extreme environments. Normally, mergers trigger starbursts, but NGC 6240's star factories are oddly muted. The culprit, those dueling black holes. Their ferocious energy output is so intense it's preventing gas from cooling into stars, effectively pressing pause on the galaxy's rebirth. Instead, we're witnessing a rare phase where black holes dominate their host galaxies, fate a preview of what might happen when our Milky Way and Andromeda collide, their own supermassive black holes destined for a similar showdown. Yet buried in this chaos lies a revelation about how the universe builds its largest structures. Most galaxies have single central black holes, but NGC 6240 proves multiple giants can coexist if only temporarily. This challenges theories that mergers inevitably lead to single consolidated cores. Some astronomers now suspect such black hole groups might have been common in the early universe when galactic collisions were more frequent. The fact that we're seeing one today suggests the universe still holds surprises about how its most massive objects grow. For now, NGC 6240 remains a laboratory for extremes, a place where gravity, radiation, and chaos collide on scales barely comprehensible. Every wavelength of light tells part of the story. Infrared reveals dust-shrouded starbirth, X-rays expose the black hole's voracious appetites, and radio telescopes trace vast outflows of material fleeing the galactic battlefield. It's a reminder that even in the universe's most destructive processes, there's beauty and knowledge waiting to be uncovered. At first glance, Stephan's quintet looks like a celestial family portrait, 5 galaxies clustered together in a cosmic snapshot. But this serene image is an illusion. In reality, 4 of these galaxies are locked in a slow-motion demolition derby, their spiral arms shredded by gravitational forces as they twist and warp each other in a dance that's lasted hundreds of millions of years. The 5th galaxy, just an innocent bystander floating nearly 3 times closer to Earth than the others, a trick of perspective that makes it appear part of the chaos. This galactic pileup, located 290 million light-years away in Pegasus, offers astronomers something extraordinary, a front-row seat to multiple collision types unfolding simultaneously. One pair, NGC 7318 and NGC 7319, are so deeply entangled their mutual gravity has ripped a 30,000 light-year-long bridge of stars between them. Nearby, NGC 7317 barrels through the group at nearly 2 million miles per hour, its high-speed passage sending shockwaves through surrounding gas clouds that glow in brilliant X-rays, a phenomenon so intense it's heated the interstellar gas to millions of degrees. These interactions have turned the quintet into a star-forming factory gone haywire. Hubble's sharp eye reveals scarlet tendrils of hydrogen gas, the raw material for new stars, stretched into bizarre shapes by competing gravitational pulls. Yet paradoxically, some regions brimming with gas show surprisingly few young stars. The reason? Turbulence from the collisions may be preventing gas clouds from collapsing into stars, like a stormy sea too rough for ships to sail. Meanwhile, other areas erupt with starbirth, their blue-white clusters sparkling like diamonds scattered across velvet. radio telescopes uncover another layer to this drama, a 50,000 light-year long stream of carbon monoxide gas, likely torn from one galaxy during a close encounter. This invisible river, chilled to near absolute zero, snakes through the group, potentially fueling future generations of stars. Even more striking are the quintet's supermassive black holes. Observations suggest at least two are actively feeding, their accretion disks glowing fiercely in X-rays as they devour gas stirred up by the collisions. One day, these monsters too may spiral together, merging in a burst of gravitational waves. Stefan's quintet isn't just a spectacle, it's a time machine. By studying how gas behaves during these complex interactions, how star formation ignites or stalls, and how black holes respond to galactic turmoil, we're glimpsing processes that shaped the early universe. This group may even foreshadow our own galaxy's fate, a preview of the Milky Way's eventual merger with Andromeda. Every strand of gas, every distorted spiral arm, every flickering black hole tells part of the story. That galaxies don't evolve in isolation, but through collisions that reshape them into something new. What makes Stefan's quintet so captivating isn't just the scale of destruction, it's how it reveals the hidden connections binding galaxies together. These aren't static islands of stars, but dynamic beings that grow, collide, and remake themselves across cosmic time. And in their tangled embrace, we see the universe's endless cycle of chaos and rebirth written large. Out in the depths of space, some collisions don't just distort galaxies, they bend light itself. The VV191 system isn't your typical galactic pileup. Instead of violent mergers or tangled arms, this pair showcases one of Einstein's most bizarre predictions in action: gravitational lensing, where a galaxy's immense gravity warps the fabric of space-time like a funhouse mirror, twisting the light from objects behind it into surreal arcs and rings. At first glance, VV191 looks like two galaxies caught mid-dance, a golden elliptical galaxy in the foreground and a delicate spiral behind it. But the magic happens where they overlap. The elliptical galaxy's gravitational field, packed with dark matter, acts like a cosmic magnifying glass, distorting the spiral's light into a faint, glowing smear that wraps around its edges. This isn't just an illusion, it's a direct snapshot of space-time curving under immense mass, a phenomenon predicted by general relativity over a century ago. What makes VV191 so special is its perfect alignment. Most lensing events involve distant quasars or galaxies too faint to study in detail. Here, Hubble's sharp vision captured both the lens, the foreground elliptical, and the lensed object, the background spiral, with stunning clarity. The spiral's distorted light reveals secrets about the elliptical's invisible dark matter halo, a ghostly structure that outweighs its stars 10 to 1. By mapping how the spiral's image stretches, astronomers can literally weigh the elliptical galaxy's unseen mass, like measuring a shadow to deduce the shape of the object casting it. But the surprises don't stop there. Peering through the elliptical galaxy's diffuse glow, Hubble spotted another gift, a streak of blue stars, likely born from gas squeezed during a previous encounter with another galaxy. This means we're seeing multiple chapters of cosmic history at once, the aftermath of an old collision preserved in the elliptical's stellar halo, and the real-time lensing of a more distant spiral. It's like finding a fossil embedded in a prism, two separate stories intertwined by gravity's relentless pull. Beyond its beauty, VV191 serves as a natural laboratory. The way its light bends helps refine our understanding of dark matter's distribution, whether it's clumpy or smooth, concentrated or diffuse. These details matter because dark matter's behavior dictates how galaxies form and evolve. Every distorted photon from the background spiral carries clues about the universe's invisible scaffolding, the hidden framework that shapes everything we see. This system also reminds us that collisions aren't always about destruction. Sometimes they're about revelation, using one galaxy's gravity as a tool to uncover secrets of another. In VV191, the real collision isn't between stars or gas, but between our expectations and the universe's endless creativity. Here, a quiet alignment of two galaxies unveils more about the cosmos' true nature than 1,000 violent mergers ever could. So the next time you hear about colliding galaxies, remember, not all cosmic crashes leave scars. Some bend light, twist perception, and hand us a lens to see the unseen. And in a universe where most of its mass hides in darkness, that's a gift more valuable than gold. The universe has a way of turning destruction into delicate choreography, and nowhere is this more evident than in NGC 4676, the mice galaxies, where two spirals entwine in a slow, inevitable embrace. Named for their long, sweeping tails that stretch across 160,000 light-years like celestial rodents scurrying through the void, these galaxies are frozen mid-collision, their dance unfolding so languidly that by the time it finishes, our sun may already have burned out. What makes the mice so mesmerizing isn't just their visual drama, but the physics etched into every starry strand. Unlike head-on crashes that trigger instant chaos, this encounter is a gravitational tango, with the galaxies' mutual pull stretching their spiral arms into tidal tails, one luminous, one faint like taffy pulled between two hands. Hubble's sharp gaze reveals these tails aren't random debris, but forensic records of the collision's history. The brighter tail, rich with blue star clusters, marks where gas compressed and ignited newborn suns, while the dimmer one trails older, redder stars exiled from their galaxy's outer disks. Zoom in closer and the details grow even richer. The galaxy's cores, still 30,000 light-years apart, are already feeling each other's influence. Dust lanes that once traced neat spiral patterns now warp into chaotic swirls, while shockwaves from colliding gas clouds spark starbursts along their overlapping edges. Yet paradoxically, the Milky's centers remain oddly calm, a reminder that galaxy collisions are less about stars crashing they're too far apart, and more about gravity reshaping entire structures over cosmic time. This slow-motion merger offers astronomers a living textbook on galactic evolution. The mice are positioned nearly edge-on from our viewpoint, giving us a clean sightline to study how tidal forces redistribute not just stars but dark matter, the invisible scaffold that makes up most of a galaxy's mass. By mapping the tail's motion, scientists can weigh the unseen gravitational forces at play, uncovering clues about how dark matter behaves during collisions. But the real magic lies in what's coming next. Over the next few 100 million years, the mice will complete their first close pass, only to swing back again and again, each encounter tightening their orbit until their supermassive black holes begin a final, furious spiral. The gas and stars torn loose today may eventually fall back into the merged galaxy, fueling future generations of stars or perhaps even forming new dwarf galaxies in the tail's wake. For now, the mice remain a snapshot of celestial patience, a reminder that in the universe's grand timeline, even apocalypses can unfold with terrible beauty. Their dance teaches us that mergers aren't just in points, but processes that can birth new structures, light new suns, and rewrite the stories of galaxies over billions of years. And somewhere in that vast, slow collision, we're glimpsing the fate of our own Milky Way, destined one day to join Andromeda in a similar embrace. NGC 520 isn't a galaxy, it's a battlefield. Caught midway through a cosmic demolition, this chaotic mashup of two spirals resembles a celestial Rorschach test, its twisted arms and glowing core telling the story of a collision that's already erased its original identities. Unlike the graceful tidal tails of the mice galaxies or the perfect ring of the cartwheel, NGC 520 is raw, unfiltered violence frozen in time, a snapshot of what happens when galaxies don't just brush past each other but slam together in a gravitational tug of war that leaves neither intact. Hubble's vision reveals the carnage in stunning detail. At first glance, you'd never guess this was once two separate galaxies. Their cores have already merged into a single, blazing heart, surrounded by a turbulent sea of dust and gas shredded into jagged filaments. One side of the wreckage glows with the blue fire of newborn stars, their formation sparked by shock waves compressing interstellar gas like a cosmic accordion. The other side trails a dark, sooty tail debris from shattered molecular clouds that will never form stars again. This asymmetry tells a forensic story. The collision wasn't a perfect head-on crash, but a lopsided impact that sent one galaxy's material spraying across intergalactic space like paint flung from a spinning brush. What makes NGC 520 scientifically priceless is its timing. We're catching it roughly 300 million years into the merger, far enough along that the galaxy's structures are unrecognizable, but early enough that their individual components haven't fully settled. It's like walking into a sculptor's studio mid-chisel, where the block of marble is neither raw stone nor finished statue, but something thrillingly in between. Radio telescopes detect vast rivers of carbon monoxide, gas, the raw material for future stars being funneled toward the center, while infrared imaging exposes dust-obscured starbursts hotter than anything in our Milky Way. Even the supermassive black holes at the galaxy's cores are feeling the strain, their feeding frenzies lighting up X-ray telescopes as they devour gas stirred up by the collision. But the real drama lies in the debris field. NGC 520's most distinctive feature is a dark, dust-laden spine that slices diagonally across its center, the last remnant of the original galaxy's disks not yet erased by the merger's chaos. This spine isn't just a relic, it's a cosmic shield, blocking radiation from the central starburst and creating bizarre pockets where gas cools inefficiently. Some regions behind it are so shielded they're essentially frozen in time, preserving conditions from before the collision like insects trapped in amber. Astronomers believe NGC 520 is a preview of our own galaxy's fate. When the Milky Way collides with Andromeda in 4 billion years, we won't form elegant tidal tails or neat rings. We'll likely look something like this, a messy, asymmetric blob radiating furious starlight as our spiral arms dissolve into chaos. Yet hidden in that chaos is a paradox. For all its violence, NGC 520's merger is also an act of creation. The same forces tearing it apart are forging new stellar nurseries, recycling metals from dead stars into future generations, and building a new galactic core that may one day anchor a giant elliptical galaxy. This is the universe's great irony. Destruction and creation are two sides of the same coin. NGC 520 doesn't just show us how galaxies die, it shows us how they're reborn. Every twisted dust lane, every blazing star cluster, every swirling river of gas is a brushstroke in a self-portrait the universe has been painting since the first galaxies formed. And in its tangled beauty, we're glimpsing the next chapter of cosmic evolution, one collision at a time. ARP 299 isn't just a pair of colliding galaxies, it's a supernova factory running at full throttle. Nestled 130 million light-years away in Ursa Major, these two spirals have been tangled in a gravitational brawl for 700 million years, and the fallout has been spectacular. While most galaxies might host one supernova every few decades, ARP 299 averages a stellar explosion every 3 months, a rate so frenetic it accounts for nearly half of all known supernova in galaxies of its type. This isn't just a collision, it's a continuous fireworks show on a cosmic scale. The secret to this explosive productivity lies in the galaxy's unique interaction. Unlike head-on crashes that trigger instantaneous chaos, ARP 299's encounter has been a slow, grinding affair, more like two celestial sandpapers rubbing against each other. As their spiral arms intertwine, vast reservoirs of gas collide, creating shock waves that compress molecular clouds into dense knots. These cosmic pressure cookers then ignite waves of massive star formation, each stellar generation living fast, burning bright, and dying young in cataclysmic explosions. Infrared telescopes reveal the staggering scale of this starbirth. Regions like NGC 3690, one of the system's two cores, churn out new stars at 30 times the rate of our Milky Way, with some clusters packing the mass of 10,000 suns into spaces just a few light-years wide. But it's the supernova that steal the show. Thanks to a coordinated effort between radio telescopes and infrared observatories, astronomers have catalogued over 20 supernovae in ARP 299 in just the past 30 years, a sample size so rich it's rewriting our understanding of how massive stars die. One standout, SN2010P, was a Type 1 supernova so close to its host galaxy's core that it illuminated previously hidden dust lanes like a flashlight beam in fog. Others, like SN1993G, were hyper-energetic events that left behind Magnetar's ultra-dense neutron stars with magnetic fields a quadrillion times stronger than Earth. The system's most intriguing feature, however, isn't something visible at all. Lurking in the brighter galaxy's core is one of the universe's most efficient supernova assembly lines, a region so choked with dust that only radio and X-ray observatories can peer inside. Here, stars form and explode hidden from optical view, their presence betrayed only by sudden flares of gamma rays or the telltale glow of radioactive nickel decay. It's a reminder that even in the most violent galactic collisions, some of the most important action happens behind cosmic curtains. What makes ARP 299 truly special is how it bridges the past and future. Its frenzied star formation mimics conditions in the early universe when galaxies were smaller and collisions more frequent. At the same time, its impending merger, likely to complete in another 500 million years, previews the fate awaiting our Milky Way and Andromeda. By studying this system, we're not just watching a galactic train wreck, we're glimpsing the processes that built the universe's first stars and will one day dictate how galaxies evolve into their twilight years. Every supernova in ARP 299 isn't just an explosion, it's a cosmic alchemist's furnace, forging heavy elements that will someday seed new planets and life. The same collisions tearing these galaxies apart are also creating the ingredients for future worlds, proving once again that in the universe's grand story, destruction and creation are chapters in the same book. Deep in the heart of the Perseus cluster, a cosmic execution is underway. NGC 1275, a galaxy caught in the fatal grip of gravity, is being slowly torn to shreds. This isn't just any galactic collision. It's a brutal dissection happening in real time, where an entire spiral galaxy is being stripped layer by layer as it plummets into the cluster's nightmarish core. Here, the violence isn't from a single impact, but from a gauntlet of forces: ram pressure, tidal stripping, and the relentless pull of a supermassive black hole 500 times heavier than the one at our Milky Way center. What makes this collision so chilling is the sheer scale of destruction. As NGC 1275 falls toward the cluster's central galaxy, it slams into the Perseus cluster's intracluster medium, a superheated plasma 10 million degrees hotter than the Sun's surface. This cosmic blowtorch scours away the galaxy's gas like sandblasting paint off metal, leaving behind eerie blue tendrils of star-forming material dangling in space like cosmic cobwebs. Hubble's sharp eye reveals these filaments, each one a stellar nursery where gas compressed by the collision ignites newborn stars, even as their parent galaxy disintegrates around them. But the real horror lurks at the center. NGC 1275's supermassive black hole, fed by the chaos, has become an engine of apocalyptic fury. Jets of plasma shoot out at nearly light speed, stretching over 20,000 light-years, long enough to bridge the distance from Earth to the Milky Way's center and back. These jets punch into the surrounding gas, creating shock waves that ripple through the cluster and sculpt enormous bubbles in the intracluster medium. X-ray telescopes capture these structures glowing like ghostly cavities, evidence of energy releases so vast they could power 1 billion galaxies. The galaxy's fate is already sealed. Simulations show its spiral arms will be completely stripped within 500 million years, leaving behind nothing but a naked core orbiting the cluster's central giant. Yet even in this destruction, there's creation. The stripped gas enriches the intracluster medium with heavy elements, while the shock waves from the black hole's outbursts may trigger star formation in other galaxies. NGC 1275 isn't just dying, it's seeding the cluster's future, proving once again that in the cosmos, every ending is also a beginning. This collision offers a grim preview of our own galaxy's destiny. Billions of years from now, the Milky Way too may fall into a cluster's heart, facing the same forces now tearing NGC 1275 apart. Its stars may one day hang as ghostly filaments in some distant core, their light a testament to the universe's endless cycle of destruction and rebirth. Billions of years from now, long after our sun has faded and the Milky Way Andromeda merger has faded into history, the universe's grand collision story will reach its final chapters. The local group, our galactic neighborhood spanning 10 million light-years, will have collapsed into a single, monstrous elliptical galaxy, a cosmic titan glowing with the accumulated starlight of 54 merged galaxies. And yet, this will be just the beginning of the end, as dark energy continues its relentless push, accelerating the expansion of space itself. Even this future mega-galaxy will eventually find itself alone in an ever-darkening void, its stars burning out one by one until nothing remains but cold, dead husks drifting in perfect silence. But the story doesn't have to end there. Depending on how the universe's deepest mysteries unfold, two ultimate collisions loom on the horizon of time. The first, known as the Big Crunch, could see gravity finally triumph over expansion. Imagine all galaxies, all matter, even the fabric of space-time itself reversing course in a cosmic contraction of unimaginable scale. Every proton, every black hole, every shred of interstellar dust would accelerate toward a single point, colliding with such force that temperatures would exceed those of the Big Bang itself. In this scenario, the universe wouldn't just end, it would rebound, potentially birthing a new cosmos in an endless cycle of collapse and rebirth. The second possibility is far quieter, yet no less profound: heat death. Here, expansion wins forever, stretching space so thin that even atoms are torn apart. Galaxies would drift beyond each other's gravitational reach, their stars exhausting every last joule of nuclear fuel until the cosmos becomes a uniform sea of particles so far apart they might as well be alone. Black holes, the universe's final survivors, would evaporate over eons via Hawking radiation, leaving behind only a faint whisper of photons cooling toward absolute zero. In this frozen, infinite night, the concept of collision itself would become meaningless. No energy left to move, no forces left to interact, just an everlasting stillness where time loses all meaning. Between these two extremes lies a haunting question: which will it be? The answer hinges on battles we can barely measure. The tug of war between dark energy's push and gravity's pull, the unknown nature of the vacuum itself, even the potential for quantum fluctuations to spawn new universes in some far future resurrection. What's certain is that collisions, the very forces that built galaxies, forged stars, and assembled the atoms in our bodies, will one day become impossible. The universe may end not with a bang, but with the last proton decaying, the last black hole dissolving, and the final light flickering out into endless expansion. Yet even in these bleak scenarios, there's a strange beauty. The same laws that govern colliding galaxies and birthing stars will dictate the cosmos' final moments, a symmetry spanning from the first fiery instant to the last fading ember. Whether the universe cycles eternally or fades into darkness, every collision we've explored, from asteroid strikes to galactic mergers, was a step in this grand narrative. Our very existence is a flicker between two unimaginable collisions: the Big Bang that began it all, and whatever final embrace or dissolution awaits at time's end. The universe doesn't just host collisions, it's built by them. From the violent birth of our moon to the slow-motion mergers of galaxies, every cataclysm we've explored reveals a cosmos that thrives on chaos, transforming destruction into creation with breathtaking precision. These 25 collisions aren't just isolated disasters, they're chapters in a grand narrative where chaos and order dance in perfect balance. The same impact that wiped out the dinosaurs cleared the stage for mammals to rise. The galactic pileups that shred spiral arms ignite starbursts bright enough to outshine entire galaxies. Even the bullet cluster's wreckage, where dark matter was caught red-handed, proves that the universe hides its greatest secrets in the aftermath of violence. Think of the atoms in your body forged in the hearts of colliding neutron stars, scattered by supernova and delivered to Earth by asteroids. The gold in your jewelry, the iron in your blood, the calcium in your bones, all were crafted in cosmic collisions billions of years before our sun flickered to life. This duality defines the universe. It destroys with one hand and builds with the other, turning catastrophe into opportunity on scales we're only beginning to understand. And the story isn't over. Right now, telescopes are capturing unprecedented details of colliding black holes through gravitational waves. Probes like JWST peer into galactic wreckage to decode how stars form in the wake of chaos. Closer to home, astronomers track near-Earth asteroids not just as threats, but as time capsules holding clues to our solar system's violent infancy. Future collisions, whether Andromeda's inevitable merger with the Milky Way or the potential smash-up of rogue planets in distant systems, will rewrite astrophysics textbooks all over again. So the next time you gaze at the night sky, remember, every serene point of light has a backstory written in chaos. The universe doesn't settle for stillness. It evolves through crashes, mergers, and explosions that shape its destiny. And as we keep exploring, each new collision we uncover won't just be an endpoint, it'll be a doorway to deeper mysteries, proving that even in the vast quiet of space, the most transformative moments come from the shattering of the old to make way for the new. The cosmos is far from finished with its demolition and rebuilding projects, and we're just beginning to witness the spectacle.